Wormholes. The very word conjures images of big cosmic tunnels bridging vast distances in space. But what if I told you that the most profound wormholes might exist in the tiniest corners of our reality? In just cubic meters of empty space, there are quadrillions of wormholes that are even smaller than quarks. It sounds unbelievable, right? According to certain theories, these tiny wormholes may actually exist and are gradually influencing space-time in ways that are not yet fully understood. These aren't fantastical space-time tunnels you probably have seen in movies. These quantum wormholes may be the unseen builders of our world, arranging the weird dance of quantum entanglement to the mysterious expansion of the universe. These might even be the crucial component that fills the largest gap in general relativity and quantum mechanics. Embark with us on a journey to the smallest dimensions of existence where the smallest things may solve the most profound mysteries. Make sure to watch to the end. I promise you'll never look at empty space the same way again. It is amazing and yet mysterious how our universe works. We are continuously discovering new mysteries to solve, from the bizarre quantum realm, where particles seem to defy logic, to the unfathomably massive structures that span billions of light years. Gravity is explained as a curvature of space-time by general relativity, which was proposed by Albert Einstein in 1915. Everything from planet orbits to the expansion of the universe can be explained by it with amazing success. On the other hand, quantum mechanics is equally effective in its domain at explaining phenomena like atomic structure and behavior of subatomic particles. However, there's a problem, a very significant one. Quantum mechanics, the legal code of the subatomic realm, is incompatible with Einstein's general relativity. The issue appears when we attempt to implement these theories within one another domains. Quantum mechanics struggles to account for the effects of gravity, while general relativity breaks down when dealing with the incredibly small scales of the quantum world. This conflict is further highlighted when we see our universe expanding faster than our current models predict. When this accelerating expansion was found in the late 1990s, it brought the idea of dark energy, a mysterious force that is pushing the universe apart. However, the calculations of the dark energy are still not quite right. It has been discovered that the universe is not only expanding, but it is expanding faster and faster. This goes against gravity, which should be gradually slowing down the expansion. Shockingly, our calculations of the amount of dark energy based on our current understanding of quantum physics produce results that are drastically different from what we observed. We are talking about a staggering 120 order of magnitude difference. That would be analogous to expecting something to be the size of a proton, when in reality it is the size of the entire observable universe. Undoubtedly, there is something missing in our knowledge. This disparity, which is sometimes referred to as the cosmological constant problem, is among the most perplexing problems in contemporary physics. It implies that we don't fully comprehend the fundamental principles underlying the operation of the universe. Several theories have been suggested to address this problem. While some advocate changing our current theories of gravity, others introduce novel and unusual exotic particles and fields. Yet none of them have completely resolved the issue in a way that satisfies the scientific community. This is where these tiny quantum wormholes come into play. In 1935, Einstein, with physicist Nathan Rosen, demonstrated that general relativity allows the possibility of bridges, also known as Einstein-Rosen bridges, could connect the two separate points in space-time. These Einstein-Rosen bridges were later dubbed wormholes by John Wheeler in 1957. In recent years, the discussion has shifted toward the existence of much smaller wormholes, commonly known as quantum wormholes. Scientists have hypothesized that the missing component of the puzzle could be the countless tiny wormholes that are responsible for dark energy. Picture yourself zooming in on empty space. Keep zooming past atoms, past subatomic particles, and past quarks, unless you reach a scale closer to our current capacity of measurement. Many physicists think that at this point, space transforms into a turbulent bubbling of quantum fluctuations. This is quantum foam. Physicist John Wheeler, who also created the terms wormhole and black hole, first proposed the idea of quantum foam in 1955. He discovered that the normally smooth fabric of space-time would turn turbulent and chaotic at incredibly small scales due to quantum effects. We are talking about the Planck scale, which is roughly 10 power minus 35 meters. To illustrate how tiny the Planck length is, consider these astonishing comparisons. It is about 20 orders of magnitude smaller than the diameter of a proton. If you were to magnify an atom to the size of the known universe, the Planck length would be no larger than a nanometer, the same size as the atom. In this quantum realm, the rules of space and time break down. Virtual particles constantly form and dissolve, existing for mere fractions of a second. These quantum fluctuations are not just theoretical, they have observable effects in our world. For example, the Casimir effect, where two uncharged metal plates in a vacuum are pushed together, is thought to be caused by quantum fluctuations. And this quantum realm might also be home to an enormous number of microscopic wormholes. The quantum scale wormholes we're discussing today might be better thought of as tiny tears in the fabric of space-time. They could potentially connect different points in space and time, or even link to higher dimensions we can't directly perceive. The key idea is that these wormholes, by their very existence, would alter the geometry of space-time on the smallest scales. And when you add up trillions upon trillions of these tiny wormholes, dark energy emerges due to quantum fluctuations of these wormholes. So just how many wormholes are we talking about? Hold on to your hats, because the numbers are staggering. The scientists estimate we'd need about 10 quadrillion microscopic wormholes per cubic meter of space, forming and dissolving every second. Just 4 cubic meters of vacuum contain approximately the same number of tiny wormholes as there are stars in the observable universe. It's an almost incomprehensible number. But remember, we're dealing with scales far smaller than atoms. At these quantum levels, such uncanny observations are not uncommon. To really understand how tiny wormholes might explain the universe's expansion, we've got to dive into some cool math. But don't worry, I'm not here to bore you with complex equations or stuffy theories, but it's worth understanding the basic framework scientists are using. When cosmologists model the universe, they use a branch of mathematics called topology. This allows them to describe the overall shape and structure of space-time. One important tool in this mathematical toolkit is something called the Gauss-Bonnet theorem. In simple terms, this theorem helps describe how the curvature of a surface relates to its overall shape. It was first developed for two-dimensional surfaces by mathematician Carl Friedrich Gauss in the 19th century. This theorem has been generalized to work in higher dimensions, making it applicable to our four-dimensional space-time. When applied to the entire universe, it becomes a crucial part of our cosmological models. Here's where things get interesting. When you introduce a high density of microscopic wormholes, it changes a specific term in the Gauss-Bonnet equation. This seemingly small tweak cascades through the math, potentially explaining the accelerated expansion we observe. In more technical terms, the scientists propose that the variation of the Gauss-Bonnet term on a manifold that has topology changes due to the formation of wormholes is not zero. This non-zero value leads to a dynamical cosmological constant. In simpler terms, it means the energy of empty space itself might not be fixed, but slowly changing over time. This dynamic nature could account for the observed effects we currently attribute to dark energy, but potentially solving two cosmic mysteries with one elegant solution. Here's how it might work. In the early universe, when space was incredibly dense and compact, the wormhole density would have been extremely high. This would have created a large, effective cosmological constant, driving rapid expansion. As the universe expanded and cooled, the wormhole density would have decreased, leading to a smaller but still significant cosmological constant. This could explain why the universe's expansion is accelerating, but not as rapidly as some theories predict. Moreover, it could help resolve the massive discrepancy between the predicted and observed values of dark energy that we mentioned earlier. By introducing this new mechanism, we might be able to bring our theoretical predictions more in line with what we actually see in the cosmos. This idea is particularly appealing because it doesn't require the introduction of new exotic forms of matter or energy. Instead, it relies on the known principles of general relativity and quantum mechanics, just applied in a new and intriguing way. The implications of this idea go far beyond just explaining the universe's expansion. If true, it could completely change our understanding of the behavior of black holes and the principles governing quantum mechanics and general relativity. Consider the picture of two particles moving in space, separated by vast distances and still strangely connected, obviously opposite to our classical intuition. This is quantum entanglement, a phenomenon that has baffled physicists for decades. Now imagine a cosmic shortcut through space-time, a tunnel connecting the universe at a very distant point. It is something that has gone into the pure realm of science fiction, but its origins can be traced back to the general theory of relativity proposed by Einstein. At first glance, these two ideas might seem as worlds apart, but what if they are closely connected? That's a notion based on what physicists Leonard Susskind and Juan Maldacena called ER is equal to EPR, referring to a deep connection between entanglement and wormholes. This conjecture might be thought of as speculation when considering every pair of entangled particles being actually connected by a minuscule wormhole, a bridge in space-time. This is a concept as beautiful as it is radical. It explains wormhole geometry can explain the spooky action at a distance of quantum entanglement. If correct, it means that the weirdness of quantum entanglement isn't just some quirk of the subatomic world, but a fundamental feature of space-time itself. Quantum wormholes might provide the key to one of the most puzzling mysteries associated with black holes, the information paradox. It develops from the discrepancy between quantum mechanics, which says information cannot be destroyed, and the classical theory of the black hole, where anything that falls into a black hole is lost forever. This is where quantum wormholes come in. These hypothetical structures might offer an exit from this paradox, quite literally. Information falling into a black hole may not get lost but could be conveyed by microscopic wormholes to somewhere else. Some theories propose that black holes are, as a matter of fact, entangled with each other, joined by a network of quantum wormholes. In principle, information swallowed up by one black hole could emerge from another, maintaining the quantum information and solving the paradox. This is related to the holographic principle, which is a very radical notion in string theory that our three-dimensional reality might only be a projection of information stored on a two-dimensional surface, something like a hologram. But if a radical new view is right, that information about what falls into a black hole might be preserved on its event horizon, encoded in a complex network of quantum entanglements and wormholes. If so, black holes, far from being cosmic trash compactors that destroy information, might be more like cosmic information scramblers. It would absorb information, process it via a very intricate network of quantum wormholes, and then dump the result quite encrypted via Hawking radiation. While the wormhole hypothesis remains quite attractive, but up to date, it has remained highly speculative. The physics world is rightly skeptical of any claim to fix such basic-like problems, and this hypothesis will have to pass through every kind of scrutiny and test before it can be acceptable. The technology to detect structures as small as these proposed wormholes is beyond our technological capability. These are phenomena at the Planck scale, about 20 orders of magnitude smaller than a proton. Our most powerful particle accelerators and detectors are nowhere near probing these scales. This raises a philosophical problem in physics. If a phenomenon is in principle undetectable, is it still a valid scientific hypothesis? Some would say that unless we can at least devise indirect ways of testing for these wormholes, the idea is more metaphysics than physics. There would be other, possibly competitive explanations regarding cosmic acceleration and dark energy, which first needed to be discredited before the wormhole hypothesis could even be accepted. Some theories modify gravity on large scales rather than introducing new elements such as dark energy or wormholes. Despite these challenges, many scientists are excited about this line of research. As Nobel laureate physicist Niels Bohr once said, "Every great and deep difficulty bears in itself its own solution." It forces us to change our thinking in order to find it. The wormhole hypothesis, even if it may ultimately prove incorrect, forces us to think about the universe in new and creative ways. Within science, ideas that turn out to be wrong can be productive. A wrong idea might reveal important gaps in existing conceptions, may lead to the design of new experiments, and even to surprising discoveries. The history of physics is full of such examples, including luminiferous ether to steady-state cosmology. That's the end of the video. Thank you for watching.